Hello, my name is Clyde Morris, and today I want to show you how we can use the ideal gas equation in a typical A-level question. Okay, so here's a typical A-level question where we're told about the amount of gas in a cylinder. We're told its temperature, its pressure, and the volume, and something called the molar mass. Okay, so let's have a look at the ideal gas equation first of all. Right, so this is the ideal gas equation here. PV is equal to nRT. And looking at the question, the thing which they're asking us to calculate, they're asking us to calculate the number of moles. Now, in this ideal gas equation, the number of moles is the n. This is the thing which they're asking us to calculate. So I think the first thing I'm going to do is I'm going to rearrange this equation to make n the subject, seeing as that's what we need to calculate. So rearranging, we see that n is equal to PV over RT. Okay. All right, so what we need to try and do is we need to look at the question, try and identify the P, the V, the R, and the T. Okay, so let's have a read. Okay, so let's try and find the pressure first of all. Okay, so it looks as if the pressure is here, and the pressure is 1.2 by 10 to the power 7 PA, 1.2 by 10 to the power 7 pascals. Okay, so let's just start plugging into this equation. So P 1.2 by 10 to the power 7 pascals. Okay, so 1.2 by 10 to the power 7 pascals. That's the pressure. Okay, so we've identified that. The next thing we need to identify is the volume, V. And if we look carefully, the volume in the question is 0.050 meters cubed. All right, so that's the volume. So let's just put that in our equation as well. 0.050. So that's the volume part of it. Okay, then we need the dividing line. Next, we need to look for the R. Now, R isn't given. R is a constant. It's called the ideal gas constant, and it's one of those things that you can look up in your exam question. There'll be a list of constants, and for an ideal gas, the ideal gas constant R is 8.31 joules per mole per Kelvin. All right, so this is the ideal gas constant. So that's the R, and we just need to put that into the equation as well. All right, so 8.31. Okay, and the only other thing that we need to work out now, that we need to include now, is the temperature. And if we look at the question, it says the temperature is 21 degrees C. Now we have to be very careful. This temperature is given in degrees C, but whenever we use the ideal gas equation, we have to change degrees C into Kelvin. And the way we do that is we add 273. So our temperature is not 21 degrees, it's 21 plus 273. And that will give us the temperature in Kelvin. And when we work that out, we find out that the temperature is 294 Kelvin. So that's the temperature which we need to use in the ideal gas equation. Right, so we just need to put that in, and that's 294. Okay, so we've got all of the various constituent parts now to help us find out n, where n is the number of moles. All right, so just plugging into the calculator, we'll find that the number of moles, once we've worked it all out, is 245.58 moles. Okay, right, so we've done the very first part of the question, working out the number of moles. All right, so let's go on to the next part of the question. Just scroll down because there's a second part to it. The next thing that they want us to find out is the mass of the air in the cylinder. So we know how many moles there are. Now we need to find out what the mass is. And of course, the mass is measured in kilograms. Now, if we look carefully at the question, let's just scroll back up to it for a second. It tells us about something called the molar mass. All right, so let's identify that for you. Okay, so the molar mass is this figure here, 0.29 kilograms per mole. This is the molar mass. And this is going to enable us to find the mass of the air in the cylinder. Okay, so let's write that figure down and see how we can work with it. All right, so molar mass is the molar mass is 0.029 kilograms per mole. This is what we had at the top of the question. And what we can do with this figure is we can have an equivalence, as we can see, between mass and the number of moles. And this is one way we can write it is like this. 1 mole, okay, this is a direct inference from the information. 1 mole is equivalent to 0.029 kilograms. All right, this is a direct inference from the molar mass. All right, okay, so this is what we can infer. Well, that's really useful, because if we know what 1 mole is, then we can work out what any number of moles is in kilograms. Okay, so 1 mole is equal to that, but we haven't got 1 mole. We have 245.58 moles. All right, so we can use that to find out how many kilograms that is, because we know what 1 mole is. All right, so let's have a go at doing that. All right, so 1 mole is equal to that. So we can say, therefore, 245.58, therefore 245.58 moles. This is what we calculated earlier on in the first part. So if we're going to multiply the left-hand side of this by 245.58, then we must do the same to the right-hand side. So we'll have 245.58 multiplied by 0.029 kilograms. Okay, so we've got moles on the left-hand side. We've got kilograms on the right-hand side. So that is going to be, once we've computed the right-hand side, that's going to give us the mass of the air. You know, this is kilograms on the right-hand side. So nearly there. So 245.58 moles, okay, which is what we worked out earlier, must be equal to the right-hand side of the equation. And when we evaluate the right-hand side of the equation, just plugging everything on the right-hand side into our calculator, we find that the right-hand side is 4.911 kilograms. So this is the mass of the air in the cylinder, which is what they've asked us to calculate. And the key to unlocking this was using the molar mass and thinking of it in this way, with this equivalence. As I say, the direct implication of the molar mass is that 1 mole is equal to 0.029 kilograms. Okay, and from that implication here in this red box, if we know what 1 mole is, we can work out what any number of moles is, and in kilograms, and we end up with this figure here. Okay, well, thanks for watching, and I hope you found that useful. Thank you.